Hello, this is Chuck Ridgway, Automation Technology Manager at Horner. Thanks for joining us for another Tuesday live stream. Well, we've got some great information for you today. Here it is. How to apply RTDs, thermocouples, and thermistors. That's right, today we're going to review the three most popular industrial temperature sensors. We're going to explain how they work, we're going to tell you how to best apply them, and we're going to give you lots of great tips on applying them properly. And along the way, through demonstration, we're going to show you how to interface these temperature sensors with a real nifty I/O system from my company, Horner Automation. We've got a lot to cover, so let's get started. So here's our agenda, and it's pretty much what I just laid out in the open. You may be wondering, why do we care how temperature sensors work? Why do I care? Just tell me how they're applied and I'm good to go. Well, what I found in 40 plus years as an application engineer is if I understand the technology I'm applying, I'll do a better job of understanding the application rules and why they are what they are. And it won't just be voodoo to me in terms of why I'm applying these particular sensors, in this case, a particular way. So it's very important with temperature sensors you understand how they work so you can apply them properly. So let's start with thermocouples. These have been around forever. They have two primary advantages. Well, let's say three. They're pretty inexpensive, or they can be, but they've got the widest temperature range and they've got the fastest response of any temperature sensor. So again, if that's important in your application, wide temperature range, fast response, then you're probably going to be using a thermocouple. Now, it's not all sunshine and roses, however. They are a little tricky to work with, which you'll discover soon, and they can be susceptible to electrical noise because the signal that they generate is quite small. Now, where are thermocouples used? Well, again, any application that really needs that high temperature range and that fast response capability, like injection molding and packaging and furnaces and other applications like that, will use thermocouples because that's really the best temperature sensor for those applications. Now let's talk about how thermocouples work. That's where we get into the little bit of the voodoo here. One thing that's interesting, at least I always have thought it's interesting, is that the thermocouple effect is something that happens when you take two differing metals and you join them at a tip. What happens is a tiny voltage is generated at the tip, and we are talking a pretty tiny voltage. And then the type of thermocouple that you would use for a given application is going to be named based on the different unique combination of materials that are used to construct that particular thermocouple. So different thermocouples with different combinations of metals will generate different voltage curves, if you will. And here's that voltage curve. And you can see that we're talking about some pretty small voltages here. In the case of some of the thermocouple types, the signal never gets above 20 millivolts, for instance. So that, again, is a pretty small voltage level we're talking about with thermocouples. Once again, I mentioned the fact that different combinations of metals will be different types of thermocouples. Here's a chart showing some of the most common thermocouple types available on the market today. And one thing that we'll talk about here in a minute is that not only do you have the thermocouple grade material, but you also have extension grade material. What is that all about? Well, we'll be covering that here shortly. Now, in terms of the most common types used from this chart, you're basically looking at type K, which is the most widely used. You can see the temperature range there. Type J and type T. Type T is very popular with really cold temperatures, for instance. Okay, now one thing you have to keep in mind when you're applying a sensor that works on the thermocouple effect is that when you connect each lead of the thermocouple probe back to your measuring instrument, could be a PLC I/O module, could be a transmitter that's converting from thermocouple to 4 to 20 milliamps, for instance. But when you make that connection to your measuring instrument, you're effectively creating another thermocouple effect. There's going to be a small voltage generated there at that junction that is technically an error because what you're really trying to measure is the temperature at the tip. All right, so you do have something called a cold junction error that has to be dealt with. Once again, that cold junction error happens at the cold junction, which is what we call the connections at the measuring instrument, with the hot junction being the area where you're trying to measure the temperature of, at the tip of the thermocouple. So any measuring instrument which is dealing with thermocouples has to handle something called cold junction compensation. So basically, it has to have a way of subtracting out that CJ error I'm shown there on the screen. And the way that is done is that an additional temperature sensor that's part of the measuring instrument will measure the temperature at the cold junction. And then based on the type of thermocouple that's connected, it will predict what that voltage loss will be. It will subtract off that voltage loss, and the result will be a reading that reflects the hot junction only. Now, in terms of wire convention with thermocouples, as the previous chart may have shown or did show, and you may have noticed, there's lots of different color codes for different types of thermocouples, but the one thing that is pretty much universal is that the negative lead from a thermocouple probe will be red. That's critical, okay? If you don't remember anything else from this presentation, remember that the negative lead is red with thermocouples, because if you connect that backwards, you're going to end up with definitely inaccurate results for sure. Okay, let's go through the installation tips now. Now we're going to talk about that extension wire. You need to make sure that the wiring that's used all the way from the probe, all the way back to the PLC or wherever the measuring instrument is located, all that wire needs to be of the same thermocouple type and thermocouple extension wire type of your probe. Okay, that's critical. Otherwise, you're going to have cold junctions out in the field that are not compensated for, and you're going to have very inaccurate readings. So that's why it's important to understand the thermocouple effect when you have to apply thermocouples. Another thing to keep in mind is you want to avoid, if possible, any large temperature gradients along the wiring from the probe back to the PLC. That will introduce some extra error. So if you can just avoid running that extension wire through some areas that have extremely high temperature gradients, then you'll be fine there. Again, I want to stress the red wire is negative. Another thing you have to pay attention to with thermocouples is grounded thermocouples versus ungrounded thermocouples. What's that all about? Well, if the hot junction is electrically conductive with the sheath that it's installed in, that is called a grounded thermocouple, because if that sheath is installed on a machine and touches metal, if you will, it's going to be conductive to that measuring junction. And there's a reason why in some applications they want it that way. And that's because if you do have a grounded thermocouple, they will respond even faster than an ungrounded thermocouple. But not all measuring instruments can handle grounded thermocouples. So make sure that if a grounded thermocouple is what you need, because you need super fast response, for instance, that you use an instrument that can handle that. Or before you purchase your thermocouple probe, if that's, if the response time isn't super critical, then make sure that you check out your measuring instrument to see what types of thermocouples it can support. Can it support grounded thermocouples or not? Okay, now I mentioned in the open that Horner has a handy dandy I/O system. The one I'm talking about is OCS-I. That's the product shown over to the right. You can use it as expansion I/O for your control system, connected to a Horner controller, whether that's one of our all-in-one controllers that has the screen and the PLC built into one piece, or whether it's one of our more traditional modular controllers that look and are applied pretty much like a traditional PLC. OCS-I is an awesome I/O system. And one of the modules with OCS-I is the ADU100. That is a universal analog input module that can handle not only 16-bit 4 to 20 milliamp and 16-bit 0 to 10 volt, it also can handle direct conversion of thermocouple and RTD readings into the system. So in the case of thermocouples, you can see there are 3 connection terminals for each channel. And in the case of thermocouples, the negative lead of the thermocouple is connected to the A input, and the positive lead is connected to the B input. So, and it's also important to note that OCS-I does support grounded thermocouples. Okay. Now let's pivot to RTDs, and RTDs stand for resistance temperature detector. So in a couple slides, it'll be pretty obvious how they work. But the advantages of RTDs are they are accurate and they are stable and they're easy to work with, relatively speaking, compared to thermocouples especially. However, they do have some disadvantages. Sometimes they can be a little bit expensive, but not always. And they do have a more limited temperature range than thermocouples do, and they don't respond quite as fast. So that's something to keep in mind with RTDs. Now, where are they used? Well, any application where that precision and stability are really important, you'll find RTDs when they don't need that super high temperature range. Food and beverage, pharmaceutical, power generation, or to just name a few of the industries. Okay, now how do RTDs work? Well, resistance temperature detectors. It makes sense that an RTD sensor, when it's exposed to different temperatures, will have a different predictable resistance value. Okay, that's how RTDs work. Now, RTDs are named for the type of material they're constructed from and for whatever the resistance value is at 0 degrees C. The most common one by far is platinum 100 or PT 100. So it's constructed of platinum and it has a resistance value of 100 ohms at 0 degrees C. And there's an IEC standard that's been in use for many years. When my career started, there was a much larger variation in terms of the number of RTDs that were available on the market. Most people have standardized for most industrial applications for PT 100s with the specification you see there on the screen. All right, when you're talking about the specific resistance range versus temperature, I've got a chart here to kind of show that. You can see it's a fairly linear relationship between those two things, resistance and temperature, again, which makes them a little bit easier to deal with than thermocouples, for instance. Okay, now one thing you do have to keep in mind with RTDs is that the wire that is connected between the RTD sensor itself and your PLC or other measuring instrument, if there's enough resistance in that wire, it can cause an error, because what you want to measure is the resistance at the hot junction or where the probe is located. You don't want the total resistance including the wire, because that's going to give you an error. So you have to compensate for that wire resistance error. And how is that done? Well, it's done through the use of what's called 3-wire or 4-wire RTDs. And in industry, 3 wires are by far the most prevalent. So with a 3-wire RTD, you have an extra wire, okay, on one side of the sensor that's used to send out a tiny current. And that tiny current is used effectively to measure the resistance of the lead wire between the measuring instrument or PLC and the sensor itself. So that's how RTD measuring devices can compensate for that lead wire resistance, by having that extra wire. Now, there are also 4-wire RTDs which have a total of 4 wires, but again, in industry, the 3 wires are by far the most prevalent. All right, in terms of the color conventions with RTDs, this isn't quite as universal as thermocouples are, but almost all, reputable RTD manufacturers are going to have red leads for the excitation leads that are on one side of the sensor and white leads for the measurement lead. Okay, so that's what you're typically going to find is 2 red leads and 1 white lead for a 3-wire RTD. When we talk installation tips, you're never going to want to use a 2-wire RTD. Okay, so it's going to be a 3-wire or a 4-wire. And if you're talking an industrial application, almost always it's going to be a 3-wire lead. You do want to keep your resistance of your lead wire connecting your measuring instrument and the probe itself at 10 ohms or below. And the easiest way to do that is to use just a decent extension wire for that purpose. So Belden 8770 or equivalent, for instance, is a 3-conductor cable for a 3-wire RTD, but it's not specific for RTDs, but it's 18-gauge wire, and its resistance per 1,000-foot rating makes it an excellent choice for use with RTD sensors as an extension wire. So that's one I can definitely recommend for you, especially if you have any distance involved, okay? Also, if you're going to be having a shielded extension cable, you're going to want to make sure that you earth that shield drain from the extension cable at the best possible ground. All else being equal, a ground away from the PLC might be best, but if the best ground happens to be close to the PLC, then ground it there instead. You never want to have a shielded cable where you don't deal with the shield drain. You're just causing that extension wire to act as an antenna in that case. How are RTDs connected to our OCS-I family through our universal analog input module? Well, you've got 3 leads on the RTD typically, and 3 leads for each channel of the ADU100. And effectively, the 2 excitation red leads connect to A and B, and the measurement white lead connects to C. All right, now let's dive into the final type we're covering today of temperature sensor, and that is a thermistor. So the advantages of a thermistor are they are dirt simple to use. They couldn't get any simpler, and they're extremely inexpensive, okay? They're very, very cheap. But they have some disadvantages, which is why they aren't extremely widely used in a lot of different applications. They really only deal with a very limited temperature range, typically within the ambient range. Their ability to resolve different temperatures really varies depending on the temperature range you're dealing with, and they're not always considered the most accurate sensor to use either. So the simplicity is great, the inexpensive nature of thermistors is great, but those do come with a price, if you will. Okay, so where are thermistors used? Well, anytime you've got an environmental temperature range and you need a low-cost sensor, like HVAC, building automation in general, appliances, and some automotive applications, thermistors are ideal because they're looking for a cheap sensor, they have a limited temperature range to measure, and thermistors fit the bill. Now, in terms of how thermistors work, they work the same way RTDs do, except their resistance values are a lot higher. So remember, with an RTD, we're talking 100 ohms at 0 degrees C. With a thermistor, we're talking 10,000 ohms at 25 degrees C. So big, big, big difference there in terms of the resistance range. And here is a chart showing an NTC thermistor, a 10K NTC thermistor, which is the most common category of thermistors that are used in industry these days. Okay, but you can see even at around 0 degrees C, you're talking 30,000 ohms of resistance there. But a very limited temperature range, obviously. You don't go up nearly as high as RTDs and thermocouples do. The most common thermistors that are in use are 10K type 3 and 10K type 2, all right? So it's very important that you make sure that you buy the right ones to match your measuring instrument. All right, now, do you need to deal with lead wire compensation with thermistors like you do with RTDs? Absolutely not. The wire resistance of the leads running out to the thermistor is basically just a round-off error. I mean, literally. So you don't need to worry about that. There's nothing special to deal with thermistors when it comes to lead wire compensation. And typically, you don't have any color convention that's all that standard with thermistors either. And they don't have a polarity. So you don't need to worry about which side you connect to plus and which side you connect to minus. Connect them either way, they'll work just fine. Now, some manufacturers that are reputable will use a gray color for the wire leads for type 3, and they'll use green color for the wire leads for type 2. And that would define the color of both wire leads, because again, it doesn't matter which way you connect them. In terms of installation tips with thermistors, they're extremely simple to deal with. You just need to make sure that if you're going to be using a thermistor, that you're talking about a temperature range that is appropriate for that type of sensor. You're going to want to make sure that if your measuring instrument supports only type 2 or only type 3, that you're going to use the appropriate thermistor type when you purchase your instrument. And again, you don't need to worry about polarity, which makes them extremely easy to deal with. In terms of connecting thermistors to the Horner OCS-I family, because it's got a wildly different ohmage range than we're talking about with RTDs, we have a dedicated module for thermistors. So it's an 8-channel thermistor input module, which we're just releasing this month, which is why we've got this video timed when it is. And it's an 8-channel thermistor input module where you can basically connect, again, either side of the thermistor leads to either terminal for each channel. And it basically supports type 3 sensors, is the type of sensors that are supported by our thermistor input module. Okay, so hopefully that was a good overview with some detail there on thermocouples, RTDs, and thermistors. All right, now let's take a look at how we can apply these with our OCS-I family. Okay, here's what's happening on the bench. We've got our CPU 300 product in this case. I remember I mentioned that OCS-I can be applied either as remote I/O for one of our all-in-one controllers, or it can be directly connected to one of our traditional PLC type products. And the CPU 300 is very much a traditional PLC in a lot of ways. The one big difference is that not only does it solve all the logic for the system, but it also handles all the graphics as well. And then the touchscreen is one of our HMI Connect touchscreens, and it's literally just a touchscreen component connected, making an electrical connection here, the same type that's used in your automobile between the touchscreens on your dash and the electronics that control them. So this is a pretty high-tech approach, but the beauty of it is if you ever need to swap out touchscreens, you can do that easily, or if you want to locate the touchscreen, pretty much anywhere outside of the panel where the PLC is mounted, that's easy to do as well. So anyway, that's our CPU 300. And we've got 2 OCS-I modules connected for this bench demonstration. that universal analog input module here and our thermistor input module there. And we've got the first 2 channels used on the universal analog input module, and just one of the 8 channels is in use for the thermistor module. Now, most of the work that's done in terms of configuration or in terms of these modules is done in configuration. So let's go ahead and take a look how configuration is done now. All right, so this is my ladder area. I don't have any logic right now in this bench demonstration. I'm just directly showing the values on the screen. So let's go into hardware configuration and take a look at how things are configured. So here is my CPU 300. I go to the local I/O tab, and here you'll find my universal analog input module and my thermistor module. So let's double click on those and take a look at how they're configured. Okay, so this is a 4-channel module. Okay, it has the ability to do filtering. If you'd like to filter the values for a little slower response and maybe a little more stability, you can do that. I've got that pretty much set to a minimal value. And then each channel, you've got the capability of selecting from a pretty wide list of sensor types. So 0 to 10 volt signals, 0 to 20 milliamp, 4 to 20 milliamp. It can even handle millivolt levels for things like, certain strain gauge type applications or load cell type applications. And then you can see it supports a whole different variety of thermocouple types, and of course, a couple different types of RTDs, Platinum 100 and Platinum 1000. But in this demonstration, I'm using Type K thermocouple, and I want to use degrees Fahrenheit as my temperature reading in this case. The values for this module are, when we're talking about temperature sensors, are reported in 10th degree increments. So if I have a 20.0 degree reading, I'll have a value of 200. That'll be reported in the input register, if you will. Okay, on the second channel, I've got a PT100 selected because I've got a Platinum 100 RTD. Again, I'm going with degrees Fahrenheit. And then I went ahead and disabled the unused channels. Why did I do this? Well, if I do that, then the module is not expecting there to be any kind of sensors connected, and it won't throw an alarm condition if that sensor is missing, okay, or not generating a signal, because it's obviously not missing. There's not supposed to be one there. Okay, so that's the configuration for the universal analog input module. And then in terms of the thermistor input module, it only supports the 10K thermistors of type 3, so there's really nothing to select from the pull-down list except thermistor or disable. And you can select between degrees F and degrees C, and this reports in hundredths of a degree increments. Not because it has any more resolution, just because it's a much more limited temperature range. So we chose that method of reporting the data. Okay, and we again got one sensor connected and the rest are disabled, so we don't get any false alarm conditions that occur in that scenario. Okay, all right, let's take a look at just real quickly what I've got going on with my demonstration on the bench. Okay, so here's my thermocouple reading. You can see I've got a thermocouple connected here, just connected to this probe here. Okay, when I touch the probe, you can see my temperature values go up as it heats up. All right, I've also got my RTD sensor connected here. Again, just measuring the ambient temperature area here in my bench area. And then I've also got my thermistor as well. Okay, so really pretty simple to apply these temperature sensors to the Horner OCS-I system. That does it for our technical content for today. If you're interested in attending factory training at Horner, we've got a couple courses scheduled for the second quarter. Go online and sign up today. There are lots of ways to interact with Horner online. There's our website, of course, at hornerautomation.com. There's our YouTube channel, where we have hundreds of videos, and there's always plenty of Horner news on LinkedIn. Next week, we've got a great topic for you. There are lots of reasons why you might want to switch away from your current I/O system to OCS-I. Maybe you're looking to reduce cost, maybe you've got obsolescence issues, or maybe delivery issues. There can be a variety of reasons. So next week, we've got a topic that's going to allow you to have a smooth transition from your current I/O system, whatever it might be, to OCS-I. Join us. If you haven't subscribed to our channel yet, don't hesitate to do so. It doesn't cost anything. And if you choose notifications when you subscribe, you'll be notified every time we go live and every time we post a new video. Okay, so until next week, let's all get out there and do some good.